So the focus on this update on fusion is on the challenge that's given to us since we're committed at this stage of the game, at least, to deuterium and tritium on tritium. You just basically can't get tritium off the shelf. Well, you can, but it costs a lot of money. And the promise of fusion is that the fuel is free. I mean, if you get deuterium, it's free. And the problem is right now, tritium is essentially only available from one and a half sources. One is that the Canadian government basically went the route of heavy water fission reactors. And as a result, tritium is produced as normal operation of the fission reactor. And they suck it out of there and sell it to people. That is, there are other uses of tritium besides fusion experiments. And the premier other source of tritium is the U.S. government, which makes tritium for bombs. But the cost of it is very expensive. So bombs, of course, doesn't matter too much. You don't need very much of it, and it does the job. Oh, sorry about that. Okay, so this is a number of slides wherever you see the Washington University logo there. That came from a presentation by this gentleman here, who I won't even try to pronounce his name, that was presented as part of a Department of Energy workshop where people were interested in fusion. That's been presented pretty much every year in the summertime. And he got the leadoff talk this last summer. So the thing that's stronger than ever is the fact that we now are having a bigger demand for energy because of the huge boom in data centers for the AI universe. And so all the predictions of what people thought we needed in power on the grid are being revised rapidly, and fusion is a perfect candidate for this because, of course, it can be plugged in onto the grid. Well, hypothetically, not available yet, but hypothetically can be plugged into the grid. You can put it into a location that's close to where your data centers and things are. And ultimately, the fuel cost should be very low. We'll talk about that a little bit later because there are some issues. Okay, so this is the basic outline. And what we'll do is talk quickly a little bit about the core of fusion science, because most of this, what we're going to talk about later in this presentation, is never been considered the core of fusion science because it has to deal with making fusion a practical way of generating electricity and doing other things. So we'll look into why we need to deal with tritium, how we got to where we are, and then we'll talk about protons and lithium and breeding. Two examples, one which is the JET experiment that just shut down, but was the biggest consumer of tritium outside of bombs in the world. The MIT Libra experiment, which is just starting up, which is going to try to understand how we can make tritium useful in a particular context of a lithium-based breeding process, lithium and beryllium actually based breeding process. We'll have some updates on fusion news as we have traditionally, and a specific update from Commonwealth Fusion on their semi-annual report on where things are, and they're making a lot of progress. And as usual, if anybody has any questions, feel free to ask them at any time. So a little bit about where did fusion science come from? Well, you can somewhat say it started many, many years ago in the BCE era, about 400 to 500 BCE, with the philosophical and sort of natural science work of several Greek philosophers. The most well-known participant in this thing is Democritus. And then we'll talk about how it advanced throughout the 19 teens to the 20s into the 30s, and then kind of went on hiatus for a little bit of time while the focus in nuclear science was on fission, and then reappeared in the 1950s. And we'll talk about specifically about the binding energy issues and look at their possible fusion reactions and the fuel issues. So again, thanks to the University of Washington and we'll call them BS, some good slides. So what are the possible viable fusion reactions? Well, there's a bunch of them, but when you start to break them down into the ease of doing them and the value energy-wise that you get from doing them, it rapidly drops from dozens to just a handful. We're focusing mostly in the fusion community right now on this DT reaction, deuterium and tritium, because it's the easiest one to set off, essentially. It gives you a nice balance in terms of the energy output. The triton and deuterium fusion produces a neutron, carries off about 80% of the energy, and about 20% of the energy is in the form of an alpha particle, which will be in all the relevant kind of confinement experiments we've been doing, useful for heating the fuel. The original effort in fusion was in the area of deuterium and deuterium because of the fact that it's just deuterium. You get that from seawater, and there's an abundant source of deuterium in the world. It does produce a triton, so that if you do deuterium and deuterium fusion, even if you're not intentionally doing tritium, you make tritium. And that tritium then, of course, will fuse with the deuterium, because any temperature that's useful for this one is easier. It basically also has a branch that does not produce the triton. So about half of the deuterium-deuterium fusion produces helium-3 and a neutron. So the breeding process is actually going to happen whether you want it or not, in some sense. This is a reaction people are talking about now because there's some belief that there's abundance amount of helium-3 on the moon. And we could go mining the moon, and then we would have this reaction, but it's much harder to ignite. It takes a lot more energy to get it going. And the one that was always the outlier, but of interest at the beginning of the fusion program, was a proton and a boron 11, because it produces no neutrons at all, but it's very hard to ignite. So just a quick look at how fusion compares to other. I like this. I never saw this one before. It's interesting. So if you have 2 million tons, these are metric tons, 2 million tons, about 21,000 rail cars, you can essentially produce the same amount of energy as you can with one little pickup truck here, half-ton pickup truck carrying a couple cylinders of gas. And that's nice, but that's kind of a lie, because that says, well, that's all deuterium, but in reality, as we'll see, there's needs for some lithium and some beryllium, or perhaps some lead or something else. So it'll take maybe 2 pickup trucks, but in any event, still very, very impressive in terms of the energy density. So a little about the history here. 430 BCE, thereabouts, this gentleman up here, Democritus, a Greek uh, natural philosopher from the area around Thrace in the Greek mainland, basically hypothesized this thing which he called an atom. Things didn't change too much for the next couple thousand years, and then in the 19th century, people started playing with electricity, and as vacuum pumps got better, they started to make discharges that had glowing effects inside of the glass, and eventually Wilhelm Conrad Röntgen pumped on the glass enough that the so-called cathode rays that people were seeing basically disappeared, and invisible rays came out of the glass. And there's the famous photograph of the first X-ray ever taken of a person. He got his wife to put her hand with her wedding ring in front of the tube, and you can see the diamond scattering some of the X-rays and the bones in her hand. This got a lot of people excited, of course, because among other things, Röntgen got the first Nobel Prize in physics. He did the work 1894, 95, and they immediately rewarded him essentially because that was pretty neat new stuff. And so that got a lot of people interested, and pretty soon other people were trying to find out a way to get a Nobel Prize in physics. And cathode rays, X-rays, and then in 1896, Henri Becquerel in France basically did an experiment that he described later as being intentional, but perhaps the original experiment was accidental. He was working on phosphorescence, and his father had given him some uranium salts that were used in some artistic endeavors and things, and he went off to the south of France for vacation, as a common thing. And he apparently left some of these uranium salts on top of some photographic plates in a drawer. When he came back, absentmindedly, he took the plates and developed them. There was stuff there that shouldn't have been there, and he said, well, maybe it's like Röntgen. And so he did some more experiments, and pretty soon other people were hearing about these experiments and got interested. The Curies, Pierre and Marie, took this idea that Becquerel had sort of brought to the surface and spent a lot of time and effort and extracted from uranium ore radium and another substance that she called polonium after her native country. Becquerel and the Curies shared the 1903 Nobel Prize in Physics. And basically, this was the first time that people had essentially broken apart Democritus's atoms. Democritus's atoms said, and this was a surprisingly modern concept, he said, all things are composed of atoms, cannot be destroyed. They're separated by the void or empty space, and they're in constant motion and undergo collisions, and constant change occurs throughout the void. That's a pretty modern concept. So suddenly we had the atom being broken apart. Now, in the middle of this period here, J.J. Thomson, who had been involved with gas discharges, suddenly realized that he was extracting from these atoms electrons. He didn't say that immediately, but later on he did. And we'll hear from him actually. Thomson, if you can hear him.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
That sounds like it was made in 1897, but actually it was made in 1934. So I was surprised when I found out when it was made, because the quality of the recording was so crappy. But be that as may. So Thomson basically then hypothesized an atom that was essentially like a British plum pudding. There was this uniform sort of mass of positive charge, and in the midst of it, there were occasional electrons that balanced out the overall charge. Well, going back to this earlier period, Ernest Rutherford, who was a very peripatetic physicist, he started off his career in New Zealand. He went to university in Cambridge, England, and J.J. Thomson actually sponsored him as the first person to essentially do undergraduate research opportunity program, almost like I got to do at MIT. And he took this idea of spontaneous radioactivity that Becquerel had uncovered and separated out what these things coming out were by using magnets and electric fields, and he called them alpha, beta, and gamma. We still call them that. These two are particles, and this one, of course, is electromagnetic wave. Rutherford basically then went to Canada at McGill University and spent a few years there, and then he was awarded for this by getting a Nobel Prize. And then he was back in England at Manchester University. And at Manchester University, he was now a highfalutin guy. And he hired these two guys, Geiger and Marsden, who are German scientists who actually worked early on with Thomson, and said, hey, we need to figure out a little bit more about what's going on with these alpha particles. And so he was interested in seeing if he could validate Thomson's model for the atom. And he had Geiger and Marsden basically build an apparatus that fired a beam of alpha particles coming from a source that was given, the availability of that idea was given to him by the Curies. And he discovered that, contrary to Thomson's model, there was a central blob of charge that was positive charge. Didn't know at first it was positive or negative, because people were already playing with the idea of orbits around the sun. And there was a cometary idea that you could have a negative charge, essentially gravitational traction, and you'd have a slingshot effect where the comet came whipping around the sun. Well, maybe the result of this experiment could be explained that way also. But later he decided it was positive charge. And this is
Put anything.
no. This is the experiment that Geiger and Marsden did as a modern interpretation of it. But what you had was a source of alpha particles that struck gold foil, very thin foil, atomically thin foil, and you then observed where the alpha particles ended up by looking at a phosphorescent screen where there will be little flashes of light when the alpha particles struck the screen, and you peered at it with a microscope. You actually do this in junior physics lab at MIT, or did when I was undergraduate. And this is what you see. Vast majority of the alpha particles just go on through because there's a lot of empty space in between the gold atoms as a whole. Some of them are deflected slightly because they enter the gold atom essentially and encounter some of the net electric field near the nucleus. The electrons that are outside where the alpha particle goes don't have any effect, but the charge is somewhat screened. But every once in a while you get one that comes off at a pretty strange angle. And Rutherford said, it was quite the most incredible event that ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. And that's not a bad analogy. This was obviously a very dramatic thing happening at that time period in the world with the naval gunnery, and it's a good analogy. This is what the experiment actually looked like at that time. So there's a vacuum in here because the alpha particles, as Rutherford found out very early on, the alpha particles are very, very limited in their passage through air. But if you pump the air out, then they pass through the vacuum reasonably well. Here's your microscope, basically, and here's the source, some radium, and then there's a little collimating system here, and this is the foil. And you rotate this thing. And Geiger and Marsden collected these data points. Now, you need to know this axis is linear, scattering angle, and this axis is logarithmic. So when you're very, very straight on, essentially going back to here, these angles in this very low angle range, a very large number of alpha particles come through. When you get out to these alpha particles that went back the other way, the number drops dramatically. And this is the thing that makes the experiment very difficult to do and very, very unpopular with students, because this is 10 to the 7th. And to get credible numbers, you want to at least be into this range down here. And that's a factor of 10,000. If you go way out and they went to about 155 or something like that in terms of the measured angle. This experiment has been done now with protons instead of with alpha particles. And there's a slight deviation from the curve. The curve is just Coulomb scattering, right? And this was the formula that Rutherford came up with, and this is the model of the atom that came out of that. Now, that had immediately problems because, of course, we understood by that time from the work of Einstein and, of course, the work earlier of Maxwell that the radiating process would have caused the electron to collapse into the nucleus because it's accelerated all the time. Later, it turns out, of course, quantum mechanics said, no, there's these orbits that are stable, and there's no extra radiation in the ground state coming out of there. So go back over here real quick. Rutherford then goes from Manchester to replace essentially Thomson at the Cambridge University Cavendish Laboratory. He then brings on some of his older people from Manchester, but he also hires a bunch of new people. And they start bombarding what he calls diplons, which we call today deuterons, uh, onto substances, both solids and also gases. And the work goes on for about more than a decade. They start the work in the late teens and go on into the early 30s. And the result is sometimes strange things happen. And earlier on, one of the guys he hired figured out that if you bombard with alpha particles beryllium, you end up with neutrons. This will be relevant to the future. One of the things that came out of this is discovery that one of the reactions you can get is tritium. They couldn't isolate tritium, and they didn't know it was radioactive. That work came along a little later by Luis Alvarez and Robert Koenig. They isolated and measured the beta decay of the tritium and its half-life. The speech that was given by the head of the Swedish Academy on the awarding of the prize in 1903 is interesting because it also has a lot of modern nature to it. The first part of the speech deals with about the observations and things. I won't go through all that, but he makes some very broad statements that presage the future to a significant extent, because he said we've gained knowledge of a property of a matter that nobody knew about, gained new methods in terms of the way to observe things, and we found a new source of energy, as he said, for which the full explanation is not yet forthcoming. And he then went on, waxed poetic, and said about a new era in the history of the physical sciences. Now we can only touch on the magnificent experiments carried out in this domain last year, and etc. And the future that stems from this. And then he points out a couple of things. One is that while the Nobel Prize was at that stage very young, it was already considered unusual for a woman to get a Nobel Prize. And he said, of course, that what the Professor and Madame Curie did was clearly no Nobel Prize winning material. And then he went on and he said that we can also recognize that they took Becquerel's ideas in a sense and essentially made them practical in some fashion, if you want to say. And then he quoted a biblical statement about the fact that the two Curies were working together. And then he said also, this learned couple represents a team of differing nationalities, a happy omen for mankind joining forces in the development of science. And of course, there was something that was novel at that stage of the game. So let's go now and see how this all fits together. Nuclear binding energy, people started to understand by the early 20s. 100 years ago, that with the nucleus that was hypothesized by Rutherford and pretty much semi-proven, you had neutrons and protons. Didn't know if it was called the neutron yet, but it was clear that you had to have something to hold the protons together from their enormous repulsion because of just all the positive charge sitting there. When you added up the mass of the nucleus and added up the mass of these individual nucleons, there was what became known as the mass deficit. Yeah, could have been a mass surplus either way, but the point was that there's a difference, and you take Einstein's formula, and that tells you how much energy is involved in holding the nucleus together. How well is the nucleus organized? So these are some of the works that gave impetus to this. This is the discovery of the neutron by Chadwick. This is a direct copy of the paper that exists on the web. And this is his little experimental apparatus. It's not too different from the Geiger and Marsden apparatus, except that now, instead of looking for flashes of light, they have an electronic detector. And this connects to an oscilloscope, which, interestingly enough, the work that Thomson did and Crookes and other people who were working on gas discharges, the cathode ray oscilloscope came out of that. And then the transmutation of effects observed with heavy hydrogen. This was some of the people that were hired again by Rutherford, and they were bombarding deuterium on deuterium, and out of this came this thing, which was the triton. So there were other people involved, and mentioned some of these in previous versions of this talk. Arthur Eddington, who's basically speculated on the nature of the energy for driving the sun and stars, 1920, based to some extent on this mass measurements that were done by Francis Aston in 1907. There's Cecilia Payne, who started off in England, ended up in Harvard, and published a doctoral thesis showing that hydrogen was the primary constituent in stars, and that fit very well with what Eddington had done. Eddington promoted her and suggested her to go to Harvard. George Gamow basically took the quantum explanation that had been developed in the past decade and introduced how that related to all this, and then this was the first measurements that were made, and then along came Hans Bethe, who worked out the detailed quantum mechanical explanation for how fusion really worked, or so we thought at the time. So going back to this binding energy, if you take the binding energy and divide it by the number of nucleons, you end up with binding energy per nucleon, which is a measure of how tightly bound the nucleus is. And this point right up here, there's the highest amount of binding energy. It's actually a little shelf here that's not shown quite here, but between iron and nickel, you can't get any tighter bind than that. So from this point on, adding more, you end up with less. And that's how we have fission, basically, because you can take this over here somewhere, uranium, and if you go back this way, you break up that nucleus, you end up with things that have sort of the average mass of the fission fragment somewhere around 118. On the other side, if you start here at hydrogen 1 And as you combine these things together, you go on up to, there's a local peak here. This is the alpha particle, very tightly bound. Then it drops down a little bit where there's a bit in the lithium and beryllium, and then you start climbing again on the way up to iron. So on this side of this line right here, you can make fusion, but for terrestrial purposes, all these things up here that happen in stellar cores and stuff are out of reach, but this range in here is accessible. So both those things will give you energy because of this mass deficit. And this was a kind of a strange way of looking at it. This, I've forgotten where this thing came out. It's about 10 or 15 years old now, but they calculate the number of joules or joules, however you want to pronounce it, that came from a particular source of fuel, and then divided it by the population needs of the average person in the U.S., which they set to be 1 unit. And with fusion, you got 676. With fission, you got 176. The primary difference between these two is not that the fusion is all that much more spectacular. It's this per kilogram of fuel number here. And the kilograms of hydrogen are just more efficient at it because they don't weigh as much as a kilogram. It's kind of a silly way of describing it. But anyway, so if we expand the binding energy per nucleon and look at the area near hydrogen, you can see there's the alpha particle peak. Then it falls back again. There's another little peak. That's another helium peak. And there's in this little shelf here for beryllium. And then it goes on up, and this is boron over here. And that's interesting, as they point out in the p boron 11 type thing. So going back to these viable fusion reactions, okay, now you can see where these energies come out of them. But now you have to figure out how do you make it practical. So we know there's positive charge. You take a accelerator and bombard one positively charged nucleus with another one. And it's been done now for over 100 years as a big relativistic heavy ion accelerator in Brookhaven laboratory in Long Island. You can easily overcome the Coulomb repulsion, but if you're dealing with the thermal thing, and that's why we call it thermonuclear fusion, you have this problem that as a proton is approaching, it's a proton on a proton. As a proton is approaching, it's climbing this hill due to the Coulomb repulsion. If you can get over the hill, you fall into this strong nuclear force. Didn't know what it was called at the time when a lot of this was happening. And that is a very strong attractor, but it has very short range. So the problem is, okay, how do you overcome this? Well, you can fire the particles from an accelerator, but if you're dealing with a thermal source, you have to have extraordinary temperatures. Or do you? We have two aces up our sleeve. The first one is Maxwell-Boltzmann distribution. That's a 19th century concept, and it just has to do with the way that the particle energies in an ideal gas basically are distributed. This is an example. This is from the solar atmosphere, and this is 100 degree Kelvin, 1200 Kelvin, and 3000 Kelvin. And you can see the shape of this thing is pretty much the same shape, but it's stretched. But the more important thing is you notice that even these are the different averages here. And you see that even though a given point here that says 3000 Kelvin, that corresponds to one of those average things, there's stuff out here. It's not easy to see because this is linear, but you can still see the color. It's still there. And when you get to 3000 Kelvin, even at lower temperatures, when you get to 3000 Kelvin, then you can obviously, there's a fair amount of stuff out there. So that helps. But still, it's a problem because the actual energy that you need is associated with temperatures in the vicinity of a billion degrees. We know that the fusion in the sun works with much lower temperatures, but the sun has some advantages in terms of the size of it and the pressure involved. But Gamow's calculation showed that there would be tunneling that could occur through the Coulomb barrier. You could just go through here. And if you did that, you see the Maxwell-Boltzmann distribution, and you see the tunneling effect. The tunneling effect is strongly dependent on energy. So as this gets better and better, but the number of available particles with the right energy drops off dramatically, that there's a little window in the middle that got named after Gamow, called the Gamow peak. And right here at this Gamow energy, you would have an option, an optimum situation. So when you do that, you can calculate the effective cross section, and that's in millibars, millibarns. And you notice it's logarithmic here and it's linear over here. Here's the DT reaction going over to helium plus a neutron. It doesn't peak until way up here, 60 kilovolts, which is a good fraction of a million degrees Kelvin. I'm sorry, billion degrees Kelvin. But there's a substantial enough amount of it going on over here that you can deal with much reduced conditions that are DT much superior by orders of magnitude to DD. DD has two branches, one that produces the triton, the other one produces the helium-3. And then there's the D helium-3, the moon mission thing. But that does require temperatures that are very close to a billion degrees. So now if you take the two most promising ones for fusion on the Earth, here's the Coulomb scattering that's going to happen in the event. And here's these two. You see that for all cases, the Coulomb scattering is much more significant than the fusion cross section. That means that only a small fraction of the collisions, even with all the good news from Gamow and stuff, are only a small fraction of those collisions are going to produce fusion. That's what leads to what's ultimately the Lawson criteria and things, that you have to hold the stuff around for a long enough period of time that even though most of them miss, every once in a while you get a fusion reaction. We'll get back to that with an interesting, another way of looking at things near the end. So now you can take the collision cross section and then imply what happens when you have the particles of different energies in the distribution function and calculate the reaction rate. And so this is now done for these different reactions. And you can see that even at a relatively low temperature, 10 15 kilovolts. That's 100 to 150 million degrees. You get a fairly significant number with DT, but these other ones much less. So why are we still stuck with tritium? Well, we just saw that the advantage of tritium over the other reactions. So we have experience with tritium, and the dominant experience with tritium was a series of experimental runs conducted with the Joint European Torus at the Culham Laboratory outside of Oxford, not Cambridge, but Oxford in England. And this was the last run, and finally shut down. Now, there was an issue that developed in the middle, of course, because England decided not to be part of the European Union, and the Culham Laboratory, however, sold its soul to Eurofusion, which is the European Union colonizing England, or something like that. This is a issue of nuclear fusion devoted to the jet, tritium, and deuterium and tritium campaign. And this is the issue they're dealing with now. How do you get rid of it? Tritium, like hydrogen, has a tendency to get inside of metals, and you have to get rid of it. There's a lot of other interesting stuff here, but let's point out that one. So the results of that experiment, though, was they produced in one shot, actually repeated a couple of times, 69 megajoules of fusion energy. And as they say, it's the most fusion energy ever produced, but it took 3 times more energy injected to heat the plasma. So this Q factor that we mentioned earlier session basically was only about a third. And that's not enough of the thing as well, because both the jet results and the National Ignition experiments at Livermore didn't include other sources of energy that were involved in the process. So in the case of Livermore, they only looked at the laser energy that was absorbed versus the fusion energy produced when they claimed that they got break even, scientific break even. But jet is a tokamak with big copper magnets, and whenever they turned those magnets on, they had to let the grid operator in England know about it, because it was hundreds of megawatts were used to run the magnets. So even the 3-to-1 for the heating was just a small fraction of the amount of energy needed. So scientific break even they might have gotten to, but energy wise, so-called engineering break even, no way. But they were happy touting the fact that the 69 megajoules of energy came from less than a quarter of a milligram of fuel. This was a system that they engineered originally in the 80s and then re-engineered again to this second set of experiments with tritium, and they called it the active gas handling system, the active being tritium being radioactive. And you can see that in addition to the torus and the immediate stuff right around the torus, there was just a huge other wing of the laboratory devoted to all the things associated with tritium, including the detritation system for the water that was used for cooling things and stuff. But here's their crowning glory here. 69 megajoules, a little over 13.5 megawatts power output from course, not converted to electricity, just heat, but coming from the fusion reactions. And this is what was said by the senior exploitation manager. Not sure what that title translates into exactly, but he said, we can reliably create fusion plasmas using the same fuel mixture to be used by commercial fusion energy power plants, which is a mixture of deuterium and tritium. And the head of the lab basically said, JET is operated as close to power plant conditions as is possible with today's facilities, and its legacy will be pervasive in all future power plants. And then they made a pitch for ITER, the giant machine in France. So the best expertise in handling tritium in the world actually comes out of the Savannah River Laboratory of the Department of Energy, and that's just all focused actually on making tritium for bombs. This presentation, which was part of that summer workshop in Princeton Plasma Physics Laboratory, goes into tritium in a great detail. Interestingly enough, if you stockpile tritium, as we have to do that to keep the bombs ready to work, it just decays at this 12-year half-life. So there are other uses of tritium, but the weapons use is the dominant one right now. Interestingly enough, where does it come from? Well, there is some produced in the upper atmosphere by cosmic rays. Same reaction, essentially, that produces the carbon-14 that we use for dating. Tritium that's in the atmosphere could be used for dating things also, different time scale. And here's the dominant source, tritium, in the world right now is neutron capture and heavy water moderators of the Canadian reactors. You can actually get it out of light water reactors as well, but it's very small amounts. And you can make it by putting specially made fuel rods into a fission reactor because there's lots of neutrons. And lithium-6 will produce tritium and helium. And then you separate it out. But in a fission reactor, you have neutrons in abundance. In a fusion reactor, you don't. For every neutron that's created by fusing deuterium and tritium, you essentially have to hang on to every one of them, or somehow or other multiply the neutrons, because each neutron has to breed another triton. The tritium, basically is kind of recycled inside. So here's your dominant DT reaction. Here's your neutron. The neutron comes over here, and this is the dominant reaction for producing more tritium. Lithium and a neutron goes over, produces a weirdly excited helium nucleus, which fragments into a normal helium alpha particle nucleus, helium-4, and a triton. And it produces actually some net energy too. So you benefit a little bit from that. But the problem is that this means you take this neutron, you react it with the lithium, and you get a triton. If you lose a few neutrons, then you get fewer tritons, and eventually your reaction will stop. So you need something to basically maintain what they call the tritium breeding ratio, or TBR, greater than 1 to count for losses. Well, how do you do that? Well, you need something that multiplies the neutrons. And it turns out there are a couple of possible things. One of them is beryllium. Beryllium has its own issues in terms of it. Supply of it is is plentiful. It's not as plentiful as the lithium, but there's plenty of it. However, you have to handle it carefully because it's poisonous. Okay, so an alternative is lead. It's a good multiplier. Uh, has its issues with handling as well. And it also produces polonium on the side. So it's not so great. You can make various compounds of some of these things. So one of the paths that's being looked at is a salt of lithium and beryllium. And you want it to be relatively non-conducting because there's magnets involved and things like that. And so you put fluorine in there and you make lithium beryllium fluoride compound salt. Well, fluorine compounds tend to be very corrosive and stuff. So there's some issues here. One of them is this mixture right here. In any event, all these things have to be handled efficiently and carefully because you don't want releases to the atmosphere. And you're going to have some releases to the atmosphere. Tritium is not a bad thing to release to the atmosphere. There's still a fair amount of it in the atmosphere left over from the nuclear testing that occurred, atmospheric nuclear testing happening back in the 50s and 60s. And it's decaying away, but there's still some there. And there's a constant release from the stack of normal power reactors and things like that, as well as the French and the Canadians and a few other countries have reprocessing plants for reprocessing their nuclear fissional fuels, and they release some tritium to the atmosphere. But you know, it's naturally there. It would take a lot of fusion reactors to equal the amount that's in the atmosphere due to cosmic rays. But you can see that there's a lot of components that have to be dealt with. You have to extract tritium coming out of the fusion chamber because, of course, a lot of the tritium is not burned in one pass. You put it in, then it comes out. You have to process all the impurities and stuff that come out as well and separate out the tritium. Then there's internal recycling. It goes on to the fusion system, and then you go into the breeding process. And as they say, fuel cycle exists because fusion burnup is low. Tritium is rare. It's radioactive. It behaves like hydrogen. And that can be an issue. So you have to store some, and then you have to figure out how to get it out of the storage. There's a whole bunch of these things. And then, of course, because just like hydrogen, it gets inside metals. But unlike normal proton hydrogen, it decays. And as it decays, it makes helium. So now you have helium getting produced inside the metal. And you start to have metal fatigue issues. Certain materials are really bad. Some of the materials that are good for other things turn out to be very bad with tritium. So here's some example here. This is from a long time ago, but this is an unexposed piece of stainless steel. And this is what happens after it's aged for 18 months. This is what happens after it's aged for 60 months. So this very nice looking needle of stainless steel basically looks pretty ugly after just 5 years. So as they point out, not all the tritium introduced comes out. Surfaces in the reaction chamber will pick up tritium. It'll diffuse in and through metals, and it then can deposit underneath other things and stuff. So they've looked at different ways of possibly extracting it from the vessel. And I have some experience, not with tritium, but and with glow discharge cleaning that we did at MIT and then at UCLA. And this is another issue that comes out of it, because if it's stuck inside the material, even after you try all this, you end up with material that will have to be treated as a radioactive source, even though it's not highly radioactive and it'll decay away fast, but it still has to be handled that way. So these were research topics that came out of a workshop on tritium that was conducted by the Department of Energy, and I won't go into the details. So to summarize what came out of that talk, safety, cost, and tritium inventory were listed as fuel cycle development issues. Then pumps, separation, all those things that basically handle the gases have to be designed to work with tritium. So this is current work that's been going on through MIT Plasma Science and Fusion Center, and also Commonwealth Fusion that's been a sponsor of it. These are a number of people involved with the founding of Commonwealth Fusion, and also more recently people who are essentially working on projects at the Fusion Center for Commonwealth Fusion, and one of them is analysis of the tritium fuel cycle. And so they call this, you can't see part of that for some reason here, a DT fusion power plant of the ARC design. And the key of the ARC design and its clever suggestion, and it hasn't been tested yet, and it won't be tested with the Spark tokamak because they're not going to be doing any breeding and stuff, is to put the vacuum vessel inside of this tank that essentially holds this molten FLIBE salt as the breeding material. So similarly to what was shown in the Savannah River presentation, this presentation from MIT basically shows all the different tasks that have to be performed in order to manage the tritium. The neutrons basically end up with three elements of things. One goes into the blanket where you want it. Some of it goes into the structure of the diverter where you don't necessarily want it. And then some of it goes to the first wall in the vacuum vessel where you don't want it for sure. And so this was one of the interesting studies that part of that MIT work. They looked at the output that you could get total as a function of time because of how long it takes for you to double the tritium in breeder blanket. And it depends on the nature of the breeder blankets, and they're promoting obviously the fact that this would work well with this lithium salt blanket. But you can see for different types of blanket structures and things, the doubling and the different rates for how much gain you could have in tritium, you can be limited in the number of output gigawatts or terawatts that you can produce just because of the shortage of tritium. Now, you could probably buy some tritium from India. India has followed a Canadian design of the CANDU reactors, and they're not selling tritium right now, but they could, and you can also enhance the output of tritium from the CANDU reactors by putting some lithium control rods inside the reactor and make tritium on purpose beyond the amount that's produced in the heavy water. So MIT then proposed this experiment called Libra, which basically is trying to keep track of all the tritium. And since they don't have a tokamak operating at MIT and that can produce any neutrons, they decided, well, you can make neutrons the old-fashioned way using an accelerator. You can buy these things commercially. They're used for well logging and for other purposes. They're a sealed unit that produces neutrons, thermonuclear neutrons. So you basically stick one of those inside of a tank of this lithium beryllium fluoride mixture, and then you measure how much tritium you can keep track of. And they promoted the idea that this design of the tank, as opposed to the kind of breeding process they're trying to do on ITER or ITER, is preferential because it means that you can make the blanket thicker. You make the blanket thicker and you get a more efficient process of converting the neutrons into tritium. And so the total tritium ratio total tritium inventory can be reduced. And that, of course, gets you up this curve faster, among other things. So this was a overall study, and this is hypothetical. Obviously, nobody really knows in some ways what these things are. But if you follow the path of ITER on to demo, which is this enormous machine that they plan to build somewhere in the world, it sucks up a lot of tritium because it's a huge machine. The fusion power is 3,000 megawatts. This is a sort of smaller version of that, almost in a sense, called Ares, and it's 500 megawatts, but it still doesn't have a very deep blanket. And so this Libra-enabled design area enables you to operate with a much higher tritium breeding ratio. Again, hypothetical. Nobody has done any of that stuff yet. So this is the Libra experiment as they have scoped it out. Here's your 14 MeV DT neutron source with the neutron. They put a neutron multiplier in here because just to get more neutrons. That's not really part of the of what would be in the breeding blanket. That extra neutron multiplier is just there to make the experiment easier. And then you basically blow extra helium gas through to collect the tritium. And well, you have to deal with all these issues here. I won't go into all of that. And this is a comparison of what Libra can do versus all the previous work that has been done with tritium breeding, and particularly the FLBE breeding process. So wherever you see an N, it's red, that doesn't quite make it. Most of these are older experiments, and or they're experiments that were done for other purposes. This FLIBE mixture basically is also considered as a coolant for fission reactors, new design fission reactors. And they came up with a plan, and the Department of Energy said that's a little too much of a jump forward. So they said, can you make something a little less exotic to start with? And they named it Baby, and they did it. And it's much smaller scale, but it sort of follows the basic concepts. And then they wrote it up in nuclear fusion. This was totally unrelated, but it popped up, and I said, this is really kind of neat because my brother's PhD work at MIT was on spin polarized hydrogen, not for fusion fuel, but turns out if you polarize the atoms as a gas, you can basically enhance the fusion cross section by a substantial amount, maybe as much as a factor 2. and that can reduce the amount of tritium that you need. It increases the burn factor, and it increases the energy in the plasma. So a lot of good things happen. And this is, again, hypothetical theory concept. This is for different scattering angles. This is the relative cross section. If you look at 1.0, that's unpolarized. And these are several different possible ways of taking advantage of polarizing either both of the source materials or just one of them and get enhancement. So I sent the thing on to my brother and said, does that make sense? Because the issue he had was how to keep the hydrogen from depolarizing, and he said, yeah, still there. But maybe it's real. Who knows? So this is some other news, and we'll kind of wrap up with this, and then give you a chance to see the video that was produced by CFS. They produce one every 6 months, basically, to let you know where they are, and it's very impressive. This is a small nuclear fusion reactor, they're calling it, even though it's maybe it's more like a device. It's a tokamak that's been built uh, in Spain and Seville, and it's basically being looked upon as a way to enhance the confinement and stability of a plasma in a tokamak, because for quite a while people realized you can make more uh, output of the tokamak if you make the circle cross section become a D shape, and that was done with a number of experiments that have culminated now with the D3 machine at General Atomic in San Diego. But if you reverse the D, which is hard to do, you get the so-called negative triangularity, and there's some benefits from that. And the only tokamak really designed for that in the world, they're doing experiments at D3, but is this one SMART in Seville. And so you can get high fusion power and extra stability. And it's just started to work. There's no tritium involved in this. It's just at this stage of the game, and probably never. But it can be done with deuterium or helium. Yeah. And these are just a sample of some of the things that are being done outside of the technical area of fusion. European Parliament held its first debate on fusion energy. FIA is the Fusion Industry Association, and so these things are kind of self-serving ones. But this is a part of the Inflation Reduction Act funding. They have gotten some revisions of the kind of regulatory environment you need for fusion, which puts fusion in the class not of a fission reactor, but more of the kind of nuclear installations that are used to produce radioactive substances for diagnostic and treatment purposes in the medical area, and for other applications like the materials testing and stuff. European Parliament and other things, that they generate a lot of reports. And I just want to throw this thing up here, and then we'll show the video of from Commonwealth Fusion, and if there's any questions, we can deal with that. So this is something that came out of the Fusion Industry Association, and they're just highlighting all outside of the plasma physics zone, all these other things that are being done by companies to make fusion more practical. So Proxima Fusion is building Starfinder, an AI-enabled stellarator optimization framework. Stellarator is becoming, again, a competitor to tokamaks. It was back 60 years ago, but it's coming back. There is work going on way of extracting tritium from the blanket. There's a number of heating technologies that are being developed. And this comment about Commonwealth Fusion, that they're exploring additive manufacturing to produce large components from some steel. So there's a lot there going on, and there is now an industry. And then we'll take a look at in December, Bob Mumgard, the CEO of Commonwealth Fusion, put out a video that shows you where things are, as I said, moving along very impressively. This is now becoming not just science, but industry. Go away.
We've had some big news over the last 6 months. One of the really big pieces, we have selected the site for the first commercial grid-scale fusion power plant. Picking the site for the first ARC focuses our efforts into a very clear next step. The fact that we're now thinking about not just the design of the plants themselves, but actually where they're going to be and how they're going to make people's lives better through energy is an evolution of the entire field. In order to get peak velocity, you have to have a great team. 6 months ago, we were ramping the Toroidal field line up. And now in our factory, the Toroidal field line, it's reached the pace that it needs to deliver Spark. It's made half of all the pancakes that will go into Spark. The next steps out of that line are actually to ship magnets to Spark to be assembled. We have another line that makes the pulsed magnets. We're starting to put together the first of the toroidal field magnets. The model coil that shows all the technology works, that was tested and it performed flawlessly. That was the last outstanding big piece of technology demonstration that we needed for Spark, and it's now done. The Spark facility is really turning into a hub of activity. Assembling equipment, putting the final touches on all the fueling pipes, the RF transmitters. Within the tokamak hall itself, people put together the equipment that will be used to assemble Spark. The large pieces of tooling that will hold the two halves of the machine, they're in place. Over the next 6 months, I'm very excited to watch the factory run, and to run on multiple lines, making magnets, shipping magnets. We're starting to see the parts of Spark itself shape up around the world. The cryostat base, the foundation of the machine. It's now on a boat, on its way here, and it will be installed in the coming months. The vacuum vessel, the largest piece of Spark, that is in its final stages of fabrication. That will be shipped here to be assembled inside the magnets. And over the next 6 months, I'm really excited. We're going to start the actual assembly of the Spark machine itself.
So if you didn't see all the highlights as he was blasting through and showing you the pictures, here's the text that describes what's going on. And they're getting ready to start putting it together. That's it.
Thanks, Ted. Can I ask a question?
Sure.
Certainly can. I've been dwelling on this. I've been dwelling on this tritium business. When you start up a reactor, is there any analogy to the old internal combustion engine or carburetor, where you had to have a choke that you need more tritium at the beginning to get it up to temperature?
Well, that's a question. It's a good question. Actually, there are people who have been doing simulations because there really is no tokamak right now that's running with tritium, and the simulations are pretty good, and they show that you could go either way. You could kind of do it by kind of puffing extra tritium in, and or possibly some of the reactor designs like jet had it, and ITER will have it, is use a neutral beam heating system in addition to other means of heating. And in a neutral beam, you could put tritium in the neutral beam. So that's one possibility. There's also a way that you ramp up very slowly with a mixture that's mostly deuterium to start with, and you gradually squirt a little tritium in over time. The problem with that is it actually consumes more tritium in the long run, though it may be advantageous in the short run because the ramp up takes time. And I think when you look at the designs of reactors based on the Commonwealth fusion work, they don't have neutral beams. They only have radio frequency heating. And as a result, you have to basically tune the ion mixture, not necessarily because the plasma part of the thing doesn't care really about the type of ions. That can helium-3 would work just as well as tritium from the standpoint of the heating because it has the same mass as the tritium does basically, and it does have an extra charge, but so there's a number of issues still that have to be addressed in that area. It's going to be a while. I mean, if Spark is on target for assembly now, they're talking about possibly having this machine assembled by the end of the summer. Then they'll start operating first of all with pure hydrogen, proton hydrogen, and then they'll start introducing helium gas into the machine. They don't want to put tritium in until they absolutely have to. And even the minute you put deuterium in at operating conditions of spark, you're making tritium in the result of that deuterium fusion that's happening. So you'll be making things radioactive and stuff. So they want to delay that as long as possible. But
another question, Ted. What struck me in this talk particularly, you talked about the polarized atoms.
yes,
How do they polarize them? How much energy is being used to do the polarization? And what is being done to try to maintain the polarization of those
yeah,
atoms?
those are all very good questions. That paper that I referenced there has some discussion of it. I have basically to depend on my brother for expertise in polarization work. Now, when he was polarizing hydrogen, they were doing it at very low temperatures, and they were doing it with very low densities, very low temperatures, and they were using lasers and magnetic fields and so the various combinations of lasers and magnetic fields can be used to polarize the hydrogen. There are a handful of different possible methods of polarizing hydrogen. The key element is in all of those cases is, does it stay polarized? And there's no experimental work yet to answer that question, though people are building experiments that will address it at some level. Probably not tritium initially because you just don't want to have to handle tritium if you don't have to. So they'll probably do it with deuterium. You can polarize the deuterium as well as the tritium. But how long does it stay polarized? Nobody really knows. There are a lot of things that can depolarize it. My brother said, you turned your back on it and it depolarized.
Larry, go ahead with your question.
I was wondering, they built Spark first, presumably because they had to answer some questions before they moved on to ARC. So what's the main questions they have to answer with Spark?
Well, Spark will be a reactor. It will generate, if of course, again, based on theoretical studies, scaling arguments, and a number of simulations and things. Spark will be a reactor. It should produce a scientific Q of maybe 10, which is enough to demonstrate that you have the guts of a reactor. 10 is a long way short, though, of what you need because of all this balance of plant equipment and stuff that has to be powered and everything like that. And you have to deal with the steam cycle and things of that nature. They're not dealing with any of the steam cycle stuff. They're just venting the heat into the atmosphere through a cooling tower. So there's no attempt to make electricity from the fusion. That's a big step between there and arc, which is actually going to be plugged into the grid. And as they just talked about it in the past month or so, they have a site now in Virginia where there's a bunch of AI data centers going in, and the local utility basically is converting a site that was a site for a coal-fired power plant into a site for a fusion plant. So that step of going from that core of the reactor to an actual functioning fusion power plant, that's still a fairly good sized step. So ARC would probably look at the spark work for the next, say, 2 or 3 years to finalize the design, and then start the construction. There may be some things you can do ahead of time, obviously, but the core design of ARC will be based on the results from Spark as an actual experimental device, but functioning as a fusion reactor. And of course, the breeding aspect is a major part of it. There's no attempt really to breed enough tritium to keep Spark operating. But there will be experiments, obviously, see how well they can deal with the handling the tritium and stuff like that.
Sounds like they're getting ahead of themselves.
Well, they want to, Mumgard is a big believer in this, blasting out the door with the, as fast as you can, get it online and such. And, that may or may not be right, but, he's the CEO of a company that has right now got a net worth of over $2 billion. So, I mean, he's has to have some sense of how they want to drive it forward. And yeah, there may be some steps along the way that they'll have to retrace. It's quite possible.
First, thanks a lot. That was very interesting talk. I really enjoyed it. Let me just present a few points from. I've worked in fusion a lot of my life, and to put arc and spark in perspective, let's say if you're ultimately going to have power, you need 3 basic things. You need the physics, you need the engineering, and you need the economics. For the first
Exactly so.
For the first 50 years or so in the program, we focused on clever plasma physics. And the outcome of that has been the tokamak, and the stellarator could be there, but it's a generation behind the tokamak, but it has some advantages. How great is the physics of the tokamak? I'd say it's okay. It'd be nice if you could design something with a factor of 3 safety factor to give you leeway. But when you actually look at the physics of the tokamak and even the stellarator, you almost have to be working at optimum performance to get the thing to work. But we've made a lot of progress, so I feel good about the physics. Now comes the engineering. So in the early days, people said, once we get the physics, don't worry, the engineers will make it work. You've raised a whole bunch of the engineering problems, and they are just about as tough as the physics problems. In particular, the tritium breeding, and then you have materials. One of my colleagues once said, everything is made of stuff. And we don't have a lot of experience with stuff being irradiated with 14 MeV neutrons. So this is another big area. And right now, I would say if you look at here, I guess it's a 50% border. Everybody has 50% gray hair or more. Those people in the community who are older are pretty skeptical of the timescales. Not that we ultimately won't solve the engineering problems, but they are really, really tough. Particularly, it's not only the breeding, which is a tough problem on its own, but you have to integrate that with the first wall, with the blanket design, with the material limitations. So I would say many of us think that we will solve the engineering problems. Not clear you're going to solve it between now and 10 years from now, which is a transition from Spark to ARC. So obviously, you notice that optimism is more prevalent with youth. And as you dig in more and more, I get, oh man, this is tough, this is tough. And the last problem, we haven't really worried about that much, is the economics. Even if you look at the simplest Dick and Jane fusion reactor, it's way bigger than a fission plant. And people say, the capital cost of fission is ridiculous. It's hard to actually envisage fusion getting that much cheaper. So that's going to be the third thing. Unless it's incredibly subsidized, it's going to take a while to figure out how to make a fusion machine cheaper.
Well, I guess I would say that, you know, not being a pure advocate of CFS, but from my you know, contact with fusion for more than 50 years, I would say probably the example that's the best example is to go from Fermi's Chicago pile number 1 to the first commercial power plants for fission in the world, and you know, that took over 10 years, but you know, part of that was an advantage of what was going on in the war, that gave them unlimited resources the first phase of the process. So the first couple, 3-4 years, they had, you know, anything they needed. Then they had to make it a bit more practical.
Dan, can you let Jeff finish his point and then?
Yeah, sure. Yeah, no, I just wanted to bring
So the
closure
thing is,
to that one aspect of it.
That's all right. Let him finish his point and then you can comment.
yeah, well, we were supposed to have a big competition between magnetic fusion and laser fusion, which was supposed to be resolved in 1984. So the timescale for fission was incredibly fast relative to fusion. Of course, in 1984, we hadn't really accomplished a diddly squat. And the basic reason from a physics point of view is with fission, the whole idea is, whoa, slow down. You're really worrying about the thing overheating or going berserk. So it's not getting too much power, it's controlling it. With fusion, it's like blowing with a match. Come on, please ignite, please ignite. And that's why it's been so much more difficult. One of the really big breakthroughs, which CFS is taking advantage of, is this development over the last few years of these Repco high-temperature superconducting magnets. We now have access to much stronger magnetic fields than many of the earlier experiments. And the high field really makes it possible to shrink the size. And if you shrink the size, then the cost goes down. I have a pretty good feeling about Spark. It'd probably take a little longer for them to make it work than they say, but compared to ETA, which seems to just, you know, its starting date increases 1 day per day. Spark is going to be ready in another year or two. And as you said, you said it exactly right. They're going to make Q equal to 10. That's their goal. And I think they've got a reasonable chance of seeing real simulation to be 8. But physics Q of 10 or so is equivalent to engineering Q of about 1. But
Is
no
that
one's
tritium
made
production you're talking about?
said,
Q, is that
Yeah.
tritium production?
Yeah. So
yeah.
It's Q.
Dan, let
Q,
him finish. Let him
Yeah.
finish.
So there'll be a good, I mean, in magnetic fusion, as you said, we've never made physics Q equal to 1. It came about 0.5 or so with JED. So getting physics Q equal to 10 is spectacular, which would be equivalent to an engineering Q of 1. That would be very, very impressive. But of course, Spark has 5-second pulses. And in any reactor like ARC, you know, you have to be running almost continuously. ARC started off being driven by by what they call RF current drive for steady state, but I think now they're thinking more of long hour-long pulses, then down for 10, 15 seconds, and et cetera, et cetera. So the engineering problems of it's going to be really tough going from spark to arc. And the older veterans in the field sort of think it's going to take longer than the 10 years they've done. On the other hand, you got to have these young gung-ho guys willing to try it. So, our hats off to them, even though we're going to be worrying. That's my comment.
Yeah, Jeff, in terms of pulses, instead of using a single device with a pulse, so you get an on-off, a square wave almost type of electricity, is it possible to have multiple small units with smaller pulses that give you, in effect, a continuum? So as one is phasing down, the other one's phasing up. So in the outside world, it seems like it's a continuous pulse, continuous flow.
Well, so there's 2 points. So first, I say the answer is no.
Yeah.
And I'll tell you what. But, if you're on for an hour and off for 15 seconds, to the outside world, it's going to look continuous because, you're making heat and you're not going to change. The heat isn't going to go on and off 15 seconds because there's a lot of thermal inertia. The other thing, making a lot of smaller ones, you sort of up the creek before you start. Because if you look at the mean free path, the 14 MeV neutrons in the blanket, it's a meter, maybe a little more. And there's nothing you can do about it. There's nothing to do with plasma physics or brilliant magnetic configurations. So no matter what, the blanket has got to be at least a meter thick. So if your blanket's a meter thick and you have a much smaller plasma, like this, you can see it's not going to be very efficient because you're not producing that much. Your volume of plasma is small. So most of the utilities, they would love to have like gigawatts power plants, fission and fusion, if they were up and running. But as you know, the problem there is if you go to build a fission plant at 1,000 megawatts, it takes forever because of all the protest, licensing, et cetera, et cetera. So I think spark and mostly fusion, in the US, there's a tendency to focus now on 200 to 300 megawatt units, if at all possible. Because then you could build them remotely, so you get the advantages of mass production, et cetera, et cetera. On the other hand, when it's all done, the fact that it's smaller, you lose on economy of scale. Like your surface to volume goes in the wrong direction for a small device.
But that leads into a regional grid as opposed, a local grid, if you will, as opposed to a regional grid, right? Which is some advantages and disadvantages to that.
Well, there's a lot of speculation, suggestions, whatever you want to call it. Professor Dennis White, who's held this series of graduate seminars essentially on fusion design for the past decade or so, which led to the founding of CFS, had one design review a year ago, and in that the students basically proposed an idea that hadn't been really thought about before, which is that once you have this hot stuff coming out of the blanket, you can essentially just store the energy there with a Rankine cycle instead of a standard steam cycle, and you can essentially then use the stored energy, thermal energy, to drive your electric generation plant. And so all you end up with is, if the pulses are shorter, the average power goes down. And in fact, it gives you the ability to throttle the power plant, which may in fact be desirable. So there's going to be a lot of ideas that will come out of the brilliant students that are out there, but it won't necessarily be fusion physics. It'll be other things. And I think that's where we don't know. And I think our speculation, and the record for speculation on the results of the physics work is uncommonly bad. But since the work that was done in Princeton, MIT, and Jet, and a couple other places in the last couple of decades. The fusion science of physics, plasma physics, in any event, has been pretty good. And I think if you follow that series of papers that they published in I guess in 2022 on the for Spark.
Yes.
Yeah. They have a tremendous database of experience, both with machine operations and also with the modeling and even some theoretical physics. And it seems to give you a good degree of confidence that you can get to Q equals somewhere between that. Their minimum side of it is 2. They're saying we're going to really try to get to 5, and it's certainly possible to get to 10. And that should give you enough confidence then, if you do get in that range, 5 to 10, that you can make a power reactor, if you can solve all those engineering issues that are just being really addressed now. So that's a plus and a minus on this thing in some ways. If you look at where they stood in terms of predicting things 3 years ago, they were a little more optimistic. But if you look at what's been done with the magnets, for instance, it's phenomenal. They are building magnets and selling magnets actually to the University of Wisconsin for use in another kind of a fusion experiment, and they're actually selling magnets. So it's it's a business now that's not just a research lab project, and I think that bodes very well for Spark Arc, because if you can make it on the scale, Spark might be 50% of the size of Arc in terms of the fusion part of the core of the thing. Then you can build these things in a factory and ship them on a barge or something like that to wherever you want to install them. And I think that changes the equation completely. You're not building the fusion equivalent of the fission monster plants that kept getting bigger and bigger and bigger and taking years and years and decades to build. If you can get that thing to the point where you build it like the rest of it is like a regular industrial plant, like a oil refinery or something like that, and you screw onto it the fusion reactor, you can change the world. And I think they have a very good shot at it. Well, that remains to be seen, of course, because there have been enough curveballs thrown to us in the past, and we've fouled them off at the very least.